Hey everyone, welcome to Geometry 2, Section 11.1, Space Figures and Cross Sections. So, by the end of this lesson, you should be able to understand the vocabulary of space figures and polyhedron. You need to know how many faces, vertices, and edges are on a given shape. You also need to know how to use Euler's formula, and you need to be able to draw a cross-section of any given shape. So let's talk about space figures. Now, when I talk about space figures, I'm not talking about these kind of space figures, although that would be fun to do, by the way, if you know anything about this guy, first person to tell me something funny about this, I'll give you a bonus point, all right? So when I talk about space figures, I'm actually talking about three-dimensional figures that take up space, all right? So it's not talking about outer space, but rather instead of a flat surface, it's something that takes up space. So here we have like an oblique triangular prism. We'll talk about what all that means, a rectangular prism, a right pentagonal prism. Just real quick, a prism is basically a shape that has two parallel bases, a top and a bottom, that are the exact same shape, and then the sides just connect those two bases. Okay, so this box right here is a rectangular prism. This cube, you could call it a square prism, okay? But we'll talk more about that later. So let's get into some vocabulary. First off, you need to know that a polyhedron is a solid figure with many plane faces, basically a three-dimensional shape that takes up space. So these were just a couple examples of that. So these are all polyhedron. A face, that's the name given to the flat surface that makes a boundary of a solid. So if we go back to a shape like this, this shape has 6 faces. And I mean, you can see the front, you can see the side, you can see the bottom. There's the back, or did I say bottom? Top, you can see the top. Let's go back. The front, the side, and the top. Okay, you can see the bottom, the left side, the back. So all 6 faces that make up this solid. The edge. An edge is a segment formed by the intersection of 2 faces. So if we go back to this same picture, that line right there is the intersection of the top and the front. So that's an edge. That's an edge. That's an edge. Okay, even this back one back here that's hidden behind the other 2 faces, when we see something that's kind of hidden behind the rest of the figure, we put a dotted line there. So you can see it's there, but it's hidden behind the other stuff. Okay? Next is the vertex, and that's quite simply what you think it would be. It's the point where 3 or more edges meet. So here on that same shape, you can see each corner is a vertex. Last thing you need to know is cross-section, and it's the intersection of a solid and a plane. So what that means is if I take a 3-dimensional object and then I were to cut it with some sort of plane, whatever you get by just holding those 2 objects up, that would be the cross-section. So let me give you an example of that. So if I were to take this cylinder and slice it horizontally, the cross-section would be a circle. Okay, if you were to take like a can and cut it, you'd see a circle. If you take a loaf of bread and then you cut off a slice, you've just created a cross-section of the loaf. So this individual slice is a cross-section representing the whole loaf. If you've ever had an MRI done or a CAT scan, they use the technology in order to get a cross-section of whatever's going on, either in your legs, in your brain, or whatever. But that's what that looks like. So it's almost as if they were to take your leg, slice it off, and then just take a look at what all's in there. Now this is an interesting diagram because it's the same shape, it's a cylinder, but you can cut it different ways and get different cross-sections. So in this first one where you cut the cylinder pretty much horizontally, you get a circle. If you cut it diagonally, you get a oval. However, if you just slice it vertically, you get a rectangle. So the direction at which you're slicing the object does make a difference as to what the cross section is. So now let's talk about faces, edges, and vertices. So here we have a shape. This would be, let's see, we'd call this a pyramid, a quadrilateral pyramid, or not quadrilateral pyramid. And what we're going to do is we're going to count how many faces there are, how many edges, and how many vertices. So we can see the first face is down here. It's the base. Then there's also that back triangle, and then this side triangle, the front triangle, the other side triangle. So altogether, that's a total of 5 faces. Now let's go ahead and talk about the edges. So let's go ahead and count. Okay, there's one edge, then there's a second, a third, a fourth. Let's count the edges along the base. So there's 5, 6, 7, 8. So there's a grand total of 8 edges. Now for the vertices, we just count how many corners there are. So there's 1 up top, 2, 3, 4, 5. Total of 5 vertices. Let's do the same thing with another shape. So this is a hexagonal prism. So let's count the number of faces. There's 1 on the top, and then on the bottom, so that's 2. And then this front is 3, 4, 5, 6, 7, 8. So there's a grand total of 8 faces. Let's count the number of edges. Now, rather than go through and count each one individually, I'm going to be smart about this. There's 6 edges along the top, so that top makes a hexagon. And then if there's 6 edges along the top, then there's 6 edges along the bottom. And then I have to do all those vertical edges. So if I count those, there's 1, 2, 3, 4, 5, 6, 6 of those. So that gives me a grand total of 18 edges. So now let's go ahead and count the vertices. So I'm going to be smart about this too. I'm not going to go through and just randomly count each vertex. But instead, let's count all the vertices up at the top. So there's 6 vertices at the top, and then 6 vertices down below. So that's a grand total of 12 vertices. Next thing I want to talk about is something called Euler's formula. It looks like Euler's or something like that, but it's pronounced Euler's. Anyways, this old dead guy came up with this idea. I'm not even sure how he did it, but came up with the idea that the number of faces plus the number of vertices equals the number of edges plus 2. So we can use this for a couple different things, but one thing I want to do is I want to verify that this works. So let's go ahead and take a look at some previous examples. So our previous pyramid here, let's plug in the numbers that we found and see, did we do it right? So the number of faces, we said there were 5 of them. There were 5 vertices, and there were 8 edges. So 5 plus 5 is 10. 8 plus 2 is 10. 10 equals 10. It's a fit. That's proof that we did it right. Let's do the same thing for the hexagonal prism. So there were 8 faces, and there were 12 vertices, and then there were 18 edges. So 8 plus 12 is 20, and 18 plus 2 is 20. So again, it works out. Proof that we did it right. Now, if you ask me, I think finding the number of faces is easy. The number of vertices is kind of easy, but doing the edges, that's kind of rough sometimes. So what we can do is we can use Euler's formula, find out what we can, and then calculate the rest. So for instance, if we were to take this figure, and let's go ahead and figure out the number of faces, the number of vertices, and then let's go ahead and calculate the number of edges. So let's do a quick count for faces. There's that triangle, another triangle, another triangle, and then the base. So that's a total of 4 faces. Let's go ahead and count the number of vertices. So there's 1 up top and then 3 below, so that's 4 vertices. So I could go through and count all the edges, but rather than that, I'll go ahead and plug those numbers into Euler's formula. So F equals 4, V equals 4, and I get 8 equals E plus 2. So I should know that there are 6 edges. And if you want to go ahead and count all those, you'll verify that indeed there are 6 edges. So let's talk about the last thing, cross sections. So again, if we have a 3-dimensional shape and we kind of slice it, what's it look like when you open up that slice? So let's say we have this bagel shape, 3-dimensional object, and if we slice it right in the middle, kind of like they do at the bagel shop, what's that look like? Well, it would quite simply look like a bagel. All right, a donut. That's what the cross section would look like. If you sliced it this way instead, you'd get 2 circles. All right, so the way you slice it determines what your cross section looks like. So here's a cone. If I were to slice the cone horizontally, it would make a circle. But if I slice it vertically and then I open it up, what would I see? It would make a triangle. Last example, what if I take a cylinder and if I were to slice it vertically, it would make a circle. But I'm slicing it horizontally, and so when I do that, if I were to take that and look, I would see a rectangle. Okay? So hopefully this makes sense to you. Hopefully this was a very easy section. If not, go ahead and get a hold of me, either email me or you can ask me questions in class. But I hope this video finds you doing well, and I will see you guys real soon. Have a good one.